Hello everyone. I'm going to discuss file system implementation, and this is chapter 14 from the book Operating System Concepts. So the following will be our outline. We will discuss file system structure, operations, and then we'll discuss about directory implementation, allocation methods, free space management, efficiency and performance, recovery, and we'll take some example of the WAFL file system. The objectives of this chapter is that at the end of this topic, you should be able to describe the details of implementing local file systems and directory structures, and discuss block allocation and free block algorithms and trade-offs. And then you'll be able to explore file system efficiency and performance issues, and then look at the recovery from file system failures. Finally, we'll try to describe the waffle file system as a concrete example. The file system provides the mechanism for online storage and access to file contents, including data and programs. And the file systems usually reside permanently on a secondary storage, and it's designed to hold a large amount of data. However, in this chapter, we are primarily concerned with issues surrounding the file storage and access on the most common secondary storage media, which is the hard disk drives and the non-volatile memory devices. So we try to explore ways to structure file use, to allocate storage space, to recover freed space, to track the locations of the data, and to interface other parts of the operating system to secondary storage. Also, throughout the chapter, we'll be considering performance issues. Alright? So, disk basically provide most of the secondary storage on which file systems are maintained, and there are two characteristics that make them convenient for their purpose. The first is to provide, or a disk can be written or rewritten in a place. Basically, it's possible to read a block from the disk, modify the block, and write it back into the same block. And a disk can access directly, okay, and any block of information it contains. Thus, it is simple to access any file, either sequentially or randomly. And switching from one file to another requires the drive moving the read-write heads and waiting for the media to rotate. Now, non-volatile memories or devices are increasingly used for file storage, and thus allocation, it's used as a location for file systems. However, they differ from the hard disks in that they cannot be rewritten in place, and they have different performance characteristics. To improve the input-output efficiency, input-output transferred or transfers between memory and mass storage, and they are performed in units of blocks, and each block on a hard drive or a hard disk drive has one or more sectors. So depending on the disk drive, sector is usually around 512 bytes or 4096 bytes. Meanwhile, the non-volatile memory devices usually have blocks of 4096 bytes, and the transfer methods are used similar to those used by the disk drives. The file systems provide efficient and convenient access to the storage device by allowing the data to be stored locally, okay, and then it's located and retrieved easily. And a file system poses two different design problems. The first problem is defining how the file system should look to the user, and this task involves defining a file and its attributes and the operations allowed on a file and the directory structure for organizing. Meanwhile, the second problem is creating algorithms and data structures to map the logical file system onto the physical secondary storage devices. The input-output control level consists of device drivers and interrupt handlers to transfer information between the main memory and this system. Now, the basic file system, which is called the block input-output subsystem in Linux, needs only to issue generic commands to the appropriate device driver to read and write blocks on the storage device. The file control block, or the FCB mentioned here, which is an inode in a Unix file system, contains information about the file. It also includes the ownership, the permissions, and location of the file contents. And the logical file system is also responsible for protection. This is an example of a layer design wherein the file system is generally composed of many different levels, and each level in the design uses the features of the lower levels to create new features for use by the higher levels. So you can see from here at the top are the application programs, and then it has the logical file system, file organizational module, basic file system, input-output control, and the devices. The input-output control level consists of device drivers and interrupt handlers, and they are to function and transfer the information between the main memory and the disk systems. And a device driver can be thought of as like a typical translator, and its input consists of high-level commands such as retrieve block 123. So basically its output consists of low-level hardware specific instructions that are used by the hardware controller, which interfaces the input-output device to the rest of the system. And the device driver usually interfaces or writes specific bit patterns to special locations. Okay, and it is used to act on and what actions to take. The file organization module knows about the files and their logical blocks or addresses, and each file's logical blocks are numbered from 0 to 1 through n, for example. Okay, and the file organization module also includes the free space manager, which tracks unallocated blocks and provides these blocks to the file organization module when requested. Finally, we have the logical file system, which is used to manage metadata information. So basically, metadata includes all of the file system structure except the actual data or contents of the files. And the logical file system manages the directory structure to provide the file organization module with the information the latter needs. Given a symbolic file name, it maintains a file structure via file control blocks. So a file control blocks, which we have mentioned earlier in an inode Unix file system, it contains information about the file and includes ownership, permission, and location of the file contents. Many file systems are in use today, and most operating systems support more than one. For example, most CD-ROM are written in the ISO 9660 format. Okay, Now, a standard format, this is a standard format agreed on by CD-ROM manufacturers. In addition to removable media, each operating system also has one or more disk-based file systems, and Unix uses the Unix file systems, or the UFS, which is based on the Berkeley Fast File System, or the FFS. Okay, Windows supports file system formats of FAT, or file allocation table. It also supports file allocation table 32 and NTFS, or Windows NT file system, and as well as CD-ROM and DVD file system formats. Right? Linux system, although Linux supports over 130 different file systems, the standard Linux file system is known as the EFS, or the Extended File System. Okay? And they have the most common versions being EX3 and EX4. Okay? They also there are also distributed file systems in which the file a file system on a server is mounted by one or more client computers across a network. And file system research continues to be an active area of operating system, especially in the design and implementation. And right now, Google created its own file system to meet the company's specific storage and retrieval needs, which include high performance access from many clients across a very large number of disks. Another interesting project is the Fuse file system, which provides flexibility in file system development and use by implementing and executing file systems as user level rather than kernel level code. So using the Fuse, a user, for example, can add a new file system to a variety of operating systems and can use that file system to manage her files. So in chapter 13 of this book, we discuss about the operating systems which implement the open function and close function system calls for processes to request access to file contents. However, in this section, we delve into the structures and operations used to implement file system operations. Now, several on-storage and in-memory structures are used to implement a file system, and these structures vary depending on the operating system and the file system, but some general principles apply. On storage, the file system may contain information about how to boot an operating system stored there, and the total number of blocks, the number and location of free blocks, the directory structure, and individual files. And many of these structures are detailed throughout the remainder of this chapter. So here we describe them briefly. For example, we have the boot control block. So the boot control block can contain information needed by the system to boot an operating system from the volume. So if the disk does not contain an operating system, this block can be empty, and it's typically the first block of a volume. In UFS or Unix file system, it's called the boot block, and in NTFS, it's called the partition boot sector. Now we also have a volume control block. Okay, it contains the volume details such as the number of blocks in the volume, okay, the size of the block, right, a free block count, and a free block pointers, as well as a free FCB pointers. Okay, and in Unix file systems, this is called a super block. Okay, while in In NTFS, it's stored in a master file table. Now, a directory structure per file system is used to organize the files. And in Unix file system, this includes the file names and associated inode numbers. But in NTFS, it's stored in the master file table. Now, a per file control block contains many details about the file, and it has a unique identifier. Okay, a unique identifier number to allow association with a directory entry. And in NTFS, this information is actually stored within the master file table using a relational database structure with a row per file. Okay, the in-memory information is used for both file system management and performance improvement via caching. And the data are loaded at mount time, updated during file system operations, and discarded at dismount. And several structures or several types of structures may be included. Shown in this figure is a typical file control block. Okay, so this is a typical file control block wherein we can see the contents of the file control block, including the file permissions, the file date such as the date of creation, date of access, and date of write. Also, it contains the file owner information, the file group, and the access control list, as well as the file size and the file data blocks or pointers to file data blocks. Now, the in-memory information is used for both file system management and performance improvement via caching, and the data are loaded at mount time. Alright, and they are updated during the file system operations, and they are also discarded at dismount. So the following are the types of structures. For example, we have an in-memory mount table which contains information about each mounted volume. So that's the mount table. And then we have an in-memory directory structure cache which holds the directory information of recently accessed directories. We also have the system wide open file table, which contains a copy of the file control block of each open file and other information. Okay, we also have a per process open file table, which contains a copy of the file control block, okay, or the pointers, sorry, to appropriate entries in the system-wide open file table, as well as other information for all the files the process has opened. We also have the buffers, okay, and these buffers hold the file system blocks when they are being read from or written to a file system. Alright? Now, in this structure or illustration, we'll see in-memory file system structures, and in letter A, you will see that, for example, a file has been created and it can be used for input-output. So it must be opened. So definitely the open system call, okay, passes a file name to the logical file system, and the open system call first searches the system-wide open file table to see if the file is already in use by another process. So basically that's the step. If it is, a per process open file table entry is created pointing to the existing system-wide open file table. And this algorithm can be saved substantial overhead. So if the file is not already open, the directory structure is searched for the given file. given file name. And parts of the directory structure are usually cached in memory, okay, to speed directory operations. And once the file is found, the file control block is copied into a system-wide open file table in the memory. And this table not only stores the file control block, but also tracks the number of processes that have the file open. So that is shown in letter B. Okay, so in the read index, or that means it's in the user space, a read index will be used here to locate for the index of the file, and the index will be searched to the per process open file table. Okay, and then it will proceed to the system-wide open file table, and then the search will continue to look onto the data blocks and file control block. The selection of directory allocation and directory management algorithm significantly affects the efficiency, performance, and reliability of the file systems. And in this section, we discuss the trade-offs involved in choosing one of these algorithms. So the first algorithm is the simplest one. This is the simplest method of implementing a directory, and it's used to use a linear list of file names with pointers to the data blocks. This method is simple to program, okay, but time consuming to execute. So what it does is, for example, to create a new file, we must first search the directory, okay, to be sure that no existing file has the same name. Okay, so what it does is that it does a linear search parameter. Okay, then we add a new entry at the end of the directory, and to delete a file, we try to search the directory for the named file and then release the space allocated to it. Now, to reuse the directory entry, we can do one of the several things. We can mark the entry as unused by assigning it a special name such as an all blank name, assigning it an invalid inode number such as 0, or by including a use/unused bit in each entry. Or we can also attach it to a list of free directory entries. Now, a third alternative is to copy the last entry in the directory into the freed location and to decrease the length of the directory. And a linked list can also be used to decrease the time required to delete a file. Now, another data structure used for a file directory is the hash table. And here, a linear list stores the directory entries, but a hash data structure is also used. And the hash table takes a value computed from the file name and returns a pointer to the file name in the linear list. So therefore, it can greatly decrease the directory, alright, search time. Okay, insertion and deletion are also fairly straightforward, although some provisions must be made for collisions. And collisions are the situations in which two file names hash, okay, to the same location. So basically, the major difficulties with the hash table are its generally fixed sizes and the dependence of the hash function on that size. Alright, also it uses a use chain overflow method. Okay, so this chained overflow hash table, which is used alternatively, wherein each hash entry can be a linked list instead of an individual value, and we can resolve collisions by adding the new entry to the linked list. The direct access nature of secondary storage gives us flexibility in this implementation of files, and in almost every case many files are stored on the same device, but the main problem is how to allocate the space to this file so that storage space is utilized effectively and files can be accessed quickly. And there are three major methods that are used in allocating the files, and they are widely used. We have the contiguous, the link, and index, and each method has advantages and disadvantages. Although some systems support all these three methods, it's more common for a system to use one method for all files within a file system type. Taking a look on the contiguous allocation, the contiguous allocation requires that each file occupy a set of contiguous blocks on the device, and device addresses a defined linear ordering on the device. And with this ordering, assuming that only one job is accessing the device, okay, accessing block B, for example, +1 after block B normally requires no head movement. Okay, so basically when head movement is needed from the last sector of one cylinder to the first sector of the next cylinder, the head need only move from one track to the next. For hard disk drives, the number of disk 6 required for accessing contiguously allocated files is minimal, okay, assuming blocks with close logical addresses are close physically as is seek time when a seek is finally needed. So basically, contiguous allocation of a file is defined by the address of the first block and length, and it's measured in block units of the file. Okay, so as you can see from the illustration, okay, so contiguous allocation is easy to implement but has limitations, and it's therefore not used in modern file systems. So you can see from here the mapping from the logical to physical, and that's around the block size of 512 bytes. So the block to be accessed will be starting from the address plus the Q, right? And the displacement into block is considered as the R. So basically, this algorithm suffer from the problem of external fragmentation, wherein as files are allocated and deleted, the free storage space is broken into little pieces, and it exists, I mean the external fragmentation exists whenever free space is broken into chunks, and it becomes a problem when the largest contiguous chunk is insufficient for a request. And since there are many drawbacks, an operating system can use a modified contiguous allocation scheme, and here a contiguous chunk of space is allocated initially. So this is what we call the extent-based system. Okay, so wherein for example, if the amount proves not to be large enough, another chunk of contiguous space known as the extent is added. That's why it's called extent-based system. So the location of a file's block is recorded as a location and a block count, plus a link to the first block of the next extent. And in some systems, the owner of the file can set the extent size, but this setting results in inefficiencies if the owner is incorrect. Okay, so basically that's the concept of extent-based system, wherein an extent is a contiguous block of disks and they are allocated for file allocation, wherein a file consists of one or more extents. We also have a link allocation method which solves all problems of contiguous allocation. And with link allocation, each file is a linked list of storage blocks, and the files or the blocks may be scattered anywhere on the device. The directory contains a pointer to the first and last blocks of the file. Right? And then to create a file, a new file, we simply create a new entry in the directory with link allocation. And each directory entry has a pointer to the first block of the file. So link allocation does have disadvantages, and the major problem is that it can be used effectively only for sequential access files. So in this example of the link allocation, a file of 5 blocks might start at block 9, so here is block 9, and continue at block 16, then block 1, then block 10, and finally block 25. So here each block contains a pointer to the next block, and these pointers are not made available to the user. Thus, if each block is 512 bytes in size and a block address requires 4 bytes, then the user sees blocks of 508 bytes. An important variation on link allocation is the use of the file allocation table, or the FAT, and this simple but efficient method of disk space allocation was used by the MS-DOS operating system, wherein a section of storage at the beginning of each volume is set aside to contain the table, and the table has one entry for each block and is indexed by a block number. The FAT is used in much the same way as a linked list, and the directory entry contains the block number of the first block of the file. Okay, so it's called the start block. Okay, and the table entry indexed by the block number contains the block number of the next block in the file, and this chain continues until it reaches the last block, which has a special end of file value as the table entry. Meanwhile, the unused block, okay, is indicated by a table value of 0. And allocating a new block to a file is simple matter of finding the first 0 valued table entry and replacing the previous end of file value with the address of the new block. The 0, okay, is replaced with the end of value file, or end of file value. Okay, so shown here is an example of the FAT structure for a file consisting of disk blocks 217, 618, and 339. Alright? And this scheme can result in a significant number of disk head 6 unless the FAT is cached. So the disk head must move to the start of the volume to read the FAT and find the location of the block in question, then move to the location of the block itself. In the worst case, both moves occur for each of the blocks, and a benefit is that random access time is improved because the disk head can find the location of any block by reading the information in the FAT. So link allocation solves the external fragmentation and size declaration problem of contiguous allocation. However, in the absence of FAT, link allocation cannot support efficient direct access since the pointers to the blocks are scattered with the blocks themselves all over the disk and must be retrieved in order. So the indexed allocation solves this problem by bringing all the pointers together into one location, and this is called the index block. Each file has its own index block, which is an array of storage block addresses. Okay, so the ith entry in the index block points to the ith block of the file. So here's an example where the directory contains the address of the index block. Okay, and to find a read the ith block, we use the pointer in the ith index block entry. So when the file is created, all pointers in the index blocks are set to null. And when the ith block is first written, a block is obtained from the free space manager and its address is put on in the ith index block entry. Now another alternative use in Unix file system is to keep the first for example, say 15 pointers of the index block in the file's inode, and the first 12 of these pointers point to the direct blocks. So they contain addresses of blocks that contain data of the file. So the data for small files of no more than 12 blocks do not need a separate index block. But if the size is 4 kilobytes, then up to 48 kilobytes of data can be accessed directly. And the next 3 pointers point to the indirect blocks. The first points to a single indirect block, which is an index block containing not data but the address of the blocks that do contain the data. And the second points to a double indirect block. Okay, so we have the single, the double, and the triple indirect plugs here. Okay, the second points to the double indirect block, which contains the address of a block that contains the addresses of blocks that contain the pointers to the actual data blocks. The last pointer contains the address of a triple indirect blocks. Okay, and under this method, the number of blocks that can be allocated to a file exceeds the amount of space addressable by the 4 byte file pointers used by many operating systems. So a 32-bit file or a 32-bit file pointer reaches only 2 raised to 32 bytes of or 4 gigabytes. And many Unix and Linux implementation now support 64-bit file pointers, which allows files and file systems to be several XB bytes in size. So the CFS file system supports the 128-bit file pointers. Now, the allocation methods that we have discussed vary in their storage capacity or storage efficiency and data block access time, and both are important criteria in selecting the proper method or methods for an operating system to implement. Now, before selecting an allocation method, we need to determine how the systems will be used. A system with mostly sequential access should not use the same method as a system with mostly random access. For any type of access, contiguous allocation requires only one access to get a block. And since we can easily keep the initial address of the file in memory, we can calculate immediately the address of the next block and read it directly. For link allocation, okay, we can also keep the address of the next block in memory and read it directly. And this method is fine for sequential access. For direct access, however, an access to the ith block might require I-block reads. Okay? And this problem indicates why link allocation should not be used for an application requiring direct access. Now, index allocation is more complex. If the index block is already in memory, then the access can be made directly. However, keeping the index block in memory requires considerable space. If this memory space is not available, then we may have to read the first index block and then the desired data block. For a two-level index, two index block reads might be necessary. And for an extremely large file, accessing a block near the end of the file would require reading in all the index block before the needed block finally could be read. Thus, the performance of index allocation depends on the index structure. Okay, so that's why it's called a more complex method. Okay. Now, some systems combine contiguous allocation with index allocation by using contiguous allocation for small files and automatically switching to an index location if the file grows large. Since most files are small and contiguous allocation is sufficient for small files, average performance can be quite good. Many other optimizations are in use given the disparity between CPU speed and disk speed. It's not unreasonable to add thousands of extra instructions to the operating system to save just a few disk head movements. And furthermore, this disparity is increasing over time to the point where hundreds of thousands of instructions could reasonably be used to optimize head movements. Now, for NVM or non-volatile memory devices, there are no disk head sinks. Okay, so different algorithms and optimizations are needed. Using an old algorithm that spends many CPU cycles trying to avoid a non-existent head movement would be very inefficient. Okay, existing files are being modified and new ones being created to attain maximum performance from the non-volatile memory storages. And these developments aim to reduce the instruction count and overall path between the storage device and the application access to the data. Now, since storage space is limited, we need to reuse the space from the deleted files for new files if possible. And to keep track of free disk space, the system maintains a free space list, and the free space list records all the free device blocks, wherein those that are not allocated to some file or directory. And to create a file, we search the free space list for the required amount of space and allocate that space to the new file. And this space is then removed from the free space list. And when a file is deleted, its space is added to the free space. And the free space list, despite its name, is not necessarily implemented as a list. Okay? So frequently, the free space list is implemented as a bitmap or a bit vector. So each block is represented by 1 bit, and if the block is free, the bit is 1. If the block is allocated, the bit is 0. Okay, so that's the legend. Okay, a 1 indicates block free, and a 0 indicates that the block is occupied. Alright, so the main advantage of this approach is its relatively simplicity and its efficiency in finding the first free block or n consecutive free blocks on the disk. And many computers supply bit manipulation instructions that can be used effectively for that purpose. Okay? Unfortunately, bit vectors are inefficient unless the entire vector is kept in main memory. So keeping it in a memory is possible for smaller devices, but not necessarily for larger ones. Okay? So for example, a 1.3 gigabyte disk with 512 byte blocks would need a bitmap of 332 kilobyte to track its free blocks. So basically, a bitmap requires extra space. So if you have a block size of 4 kilobytes, which is around 2 raised to 12 bytes, it needs a size of a disk with 1 terabyte or 2 raised to 40 bytes. Okay? So this is the amount of space needed to store its bitmap. So given that this size and for example, it constantly increases, the problem with bit vectors will continue to escalate as well, right? However, it's very easy to implement to get contiguous files. Now, another approach to free space management is to link together all the free blocks. Okay, and keeping a pointer to the first free block in a special location in the file system and caching it in the memory. So the first block contains a pointer to the next free block and so on. Okay? So in this example, we have a free space list head with the blocks 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, and then we have 17, 18, 25, 26, and 27 were free, and that the rest of the blocks were all allocated. So in this situation, we would keep a pointer to block 2 as the first free block. Okay? And block 2 would contain a pointer to block 3, which would point to block 4, which would point to block 5, which would point to block 8, and so on. And this scheme is not efficient. To traverse the list, we must read each block, and which requires substantial input-output time on hard disk drives. Fortunately, however, traversing the free list is not a frequent action. So usually the operating system simply needs a free block so that it can allocate that block to a file. So the first block in the free list is used, and the FAT method incorporates free block accounting into the allocation data structure, and no separate method is needed. Now, a modification of the free list approach stores the addresses of n number of free blocks in the first free block. So the first, we can call it n-1 of these blocks are actually free, and the last block contains the addresses of another n number of free blocks and so on. And the addresses of a large number of free blocks can now be found quickly, unlike the situation when the standard linked list approach is used. Another approach takes advantage of the fact that generally several contiguous blocks may be allocated or freed simultaneously, particularly when space is allocated with the contiguous allocation algorithm or through clustering. Thus, rather than keeping a list of n number of free blocks addresses, we can keep the addresses of the first free block and the number n of free contiguous blocks that follow the first block. And each entry in the free space list, okay, has it will list the list will contain a device address and the counts. Okay, and although each entry requires more space than would a simple disk address, the overall list is shorter as long as the count is generally greater than 1. And note that this method of tracking free space is similar to the extent method of allocating blocks. And these entries can be stored in a balance tree rather than a linked list, and for efficient lookup, insertion, and deletion. The Oracle CFS file system, which is commonly found in Solaris and some other operating systems, was designed to encompass huge number of files, directories, and even file systems. And in CFS, we can create file system hierarchies. And on these scales, metadata, input-output, can have a large performance impact. Consider, for example, that if the free space list is implemented as a bitmap, bitmaps must be modified both when blocks are allocated and when they are freed. So freeing 1 gigabyte of data on a 1 terabyte disk could cause thousands of blocks of bitmaps to be updated. And because those data blocks could be scattered over the entire disk, clearly the data structures for such system could be large and inefficient. And its management of free space, CFS, uses a combination of techniques to control the size of data structures and minimize the input-output needed to manage those structures. First, CFS creates metaslabs, okay, to divide the space on the device into chunks of manageable size. Okay? And a given volume may contain hundreds of metaslabs. And each metaslabs has an associated space map. And CFS uses the counting algorithm to store information about free blocks rather than write counting structure to disk. And it uses a log structured file system technique, okay, to record them. So basically, the space map is a log of all the block activity which is used for allocating and freeing in time order or in time or counting format. Okay? So when CFS decides to allocate or free space from a metaslab, it loads the associated space map into memory in a balanced tree structure. And this is used for very efficient operation. Index by the offset and replace the log into that structure. Okay? Now, the CFS also condenses the map as much as possible by combining contiguous free blocks into a single entry. Okay? Finally, the free space list is updated on the disk as part of the transaction-oriented operations of the CFS. And during the collection and sorting phase, block requests can still happen. And CFS satisfies these requests from the log. In essence, the log plus the balance tree is the free list. Hard disk drives and other storage media that allow blocks to be overwritten for updates need only the free list for managing free space. Now, blocks do not need to be treated specially when they are freed. Okay? And a freed block typically keeps its data but without any file pointers to the block until the data are overwritten when the block is next allocated. And storage devices that do not allow overwrites, such as the non-volatile memory devices or flash-based storage devices, they suffer badly when these algorithms are applied. Okay, because these devices must be erased before they can again be written to, and that those erases must be made in large chunks of blocks or can be composed of pages and can take relatively long time compared with reads or writes. Now, a new mechanism is needed to allow the file system to inform the storage device that a page is free and can be considered for erasure. And that mechanism varies based on the storage controller. Okay? For ATA attached device, it is trim. Okay? While for NVMe based storage, it is the unallocated command. So whatever the specific controller command, this mechanism keeps storage space available for writing. And without such a capability, the storage device gets full and needs garbage collection and block erasure. Okay, leading to the decrease in storage input-output write performance, which we know as a write cliff. Now that we have discussed various block allocation and directory management options, we can further consider their effect on performance and efficient storage use. The disks tend to represent a major bottleneck in system performance since they are the slowest main computer component. And even non-volatile memory devices are slow compared with CPU and main memory. So their performance must be optimized as well. So in this section, we discuss a variety of techniques used to improve the efficiency and performance of secondary storage. The efficient use of storage device space depends heavily on the allocation and directory algorithms in use. For example, UNIX inodes are pre-allocated on a volume, and even an empty disk has a percentage of its space loss to inodes. However, by pre-allocating the inodes and spreading them across the volume, we can improve the file system's performance. And this improved performance results from the UNIX allocation and free space algorithm, which try to keep a file's data blocks near the file inode block to reduce the seek time. Now, even after the basic file system algorithms have been selected, we can still improve performance in several ways. And some systems may maintain a separate section of main memory for a buffer cache, okay, where blocks are kept under the assumption that they will be used again shortly. Other systems cache file data using a page cache, and the page cache uses virtual memory techniques to cache the file data as pages rather than a file system oriented blocks. The caching file data using virtual addresses is far more efficient than caching through physical disk blocks. Okay, and several systems, including Solaris, Linux, and Windows, they use page caching to cache both process pages and file data, and this is known as the unified virtual memory. Now, some versions of Unix and Linux provide a unified buffer cache. Okay, so the page cache and the device drivers have some interesting interactions. So when small amount of data are written to a file, the pages are buffered, okay, in the cache, and the storage device driver sorts its output queue according to the device address. And these two actions allow a disk driver to minimize disk head 6. So basically, the page cache are just cache pages rather than disk blocks using the virtual memory techniques and addresses. It is also used to memory map the input-output page cache, and this routine input-output through the file system, which uses the buffer or the disk cache. Now, in this illustration, we can see the read and write system calls go through the buffer cache, okay, and the memory mapping call, however, requires using two cache, and these are the page cache and the buffer cache. Okay, a memory mapping proceeds by reading in the disk blocks from the file system and storing them in the buffer cache. Alright, and because the memory, the virtual memory system does not interface with the buffer cache, the contents of the file in a buffer cache must be copied into the page cache, and this situation is called as double caching, which requires caching file system data twice. So not only does this waste memory, but it also wastes significant CPU and input-output cycles due to the extra data movement within the system memory. Now, in contrast, this is an illustration wherein an input is using a unified buffer cache. So in this situation, you can see the read and write system calls use the same page cache. Okay, and this has the benefit of avoiding double caching because it allows the virtual memory system to manage the file system data. Alright, so this is an example of a unified buffer cache. Now, files and directories are kept both in main memory and on the storage volume, and care must be taken to ensure that a system failure does not result in loss of data or in data inconsistencies. So a system crash can cause inconsistencies among on-storage file system data structures such as the directory structures, free block pointers, and the free file content block. Okay, so basically, to be able to recover, there is a mechanism that is used for consistency checking, which is used to compare the data in directory structure with the data blocks on disk, and it also tries to fix inconsistencies, although it can be slow and sometimes it's not a guarantee that it will succeed. Now, some system programs are used to back up data from the disk to another storage device, for example magnetic tape or other magnetic disk or optical disk. Okay, and then the last option could be to recover the lost file or disk by recovering or restoring the data from the backup. Some examples of the consistency checker, these are system programs. For example, in Unix they have what they call the FSCK, or the file system check, which compares the data in the directory and other metadata with the state on the storage and tries to fix any inconsistencies it finds. Alright, so the allocation and pre-management algorithms dictate what types of problems the checker can find, how successful it will be in fixing them. Okay, the other types of algorithms and technologies that are used for recovery is the log structured file system, wherein a database log-based recovery algorithm is applied to the problem of consistency checking. So the resulting implementation is known as the log-based transaction-oriented or journaling file systems, and it's used to record each metadata update to the file system as a transaction. In this log structure file systems, all transactions are written to a log. Okay, and a transaction is considered committed once it's written to the log, and it is written sequentially. Alright, sometimes it is written to a separate device or a section of the disk, and it may need that the file system may need it to be updated. Okay, the transactions in the log are asynchronously written to the file system structures. Okay, so that is why it's needed to be updated. So when the file system structures are modified, the transaction is removed from the log. Now, when the file system crashes, all the remaining transactions in the log must still be performed, and this log structured file system performs faster recovery from crash, and it removes chance of inconsistencies of the metadata. Another alternative to consistency is employed by the network applications or appliance. This is from the network appliance filers, and it's called the write anywhere file layout, or the waffle file system. Okay, this is used for distributed file system appliances. So this system never overwrite blocks with new data. Rather, a transaction writes all the data and metadata changes to a new block. So when the transaction is complete, the metadata structure that pointed to the old version of these blocks are updated to point to the new blocks. And the file system can be removed, or can remove the old pointers and the old blocks and make them available for reuse. Now, if old pointers and blocks are kept, a snapshot is created. Okay, and the snapshot is a view of the file system at a specific point in time. And this solution should require no consistency checking. Okay, if the pointer update is done atomically. Waffle does have a consistency checker. Okay, however, some failure scenarios can still cause metadata corruption. So the file system is similar to the Berkeley fast file system with many modifications. So here's a waffle file layout. So basically, as you can see from this figure, it's a block based and use inodes to describe the files, and each inode contains 16 pointers to the blocks or indirect blocks belonging to the file described by the inode. And each file system has a root inode. Okay, and all of the metadata lives in the files. Okay, all inodes are in one file, and the free block map in another, and the free inode map in the third. Okay, and because these are standard files, the data blocks are not limited in location and can be placed anywhere. If a file system is expanded by addition of disks, the length of the net metadata files are automatically expanded by the file system. Thus, the waffle file system is a tree of blocks with the root inode as its base. And to take a snapshot, waffle creates a copy of the root inode, and any file or metadata updates after that go to new blocks rather than overwriting their existing blocks. Okay, so here's a representation of the snapshots in waffle. In letter A, you will see the illustration of the root inode corresponding to typical blocks, and this is before a snapshot is taken. So if a new snapshot is created, so this new snapshot will create a copy pointing to the blocks. Okay, this is the snapshot before any blocks change. Now this is the third illustration wherein block D has changed. Now here there are no changes, however this time there is a change in block D. So therefore D now will be D is now different from the original D because it has a prime here indicating that there is a change that happened on block D. Alright? Now another example is the Apple file system, or the APFS, which has a good example of the design, and its goal is to run on all current Apple devices. Okay, from the iPhone to the Mac computers, etc. So basically, some of the features that are available for the Apple file system is the space sharing, wherein a CFS-like feature in which storage is available as one or more large free spaces or containers. So there is also what we call a fast directory sizing, which provides quick use space calculation and updating. Also available is the atomic save, which is a primitive available via API, not via file system, and it performs renames of files, bundles of files, and directories as single atomic operations. So Apple chose not to implement RAID as part of the new APFS. Instead, depending on the existing Apple RAID volume mechanism for software RAID. So APFS is also compatible with HFS Plus, allowing easy conversion for existing deployments. So in this chapter, we learned that most file system resides on the secondary storage, and the most common secondary storage is the hard disk drive, but now non-volatile memory devices are increasing. Storage devices are segmented into partitions, as we have learned from here, and this is used to control the media use and allow multiple file system on a single device. Now, file systems are often implemented in layered or modular structure. The lower levels deals with the physical properties, and the upper deals with the symbolic file names and logical properties of the file. Now, the various files within a file system can be allocated space on the storage device in three ways. So we have studied the continuous, link, or index allocation. Free space allocation methods also influences the efficiency of this space. And then we discuss about directory management routines to consider efficiency, performance, and reliability. Okay, and then we included, in the last part, we included the waffle file system, which is an example of optimization of performance to match a specific input and output load, as well as the Apple file system. Okay, so that's it. So we're done with chapter 14. Thank you.